Hello, North Tahoe High. We are going to go over a real quick YouTube video on the idea of chemical equilibrium reverse reactions. What do we need to know to do well on a test? Okay, here we go again. So what we're going to take a look at is this idea in the context of our M&M lab. Let's take a look at those real simple results that we found with that first simulation. If you remember, we started with 40 M&Ms of reactants and 0 M&Ms of products, so a lot more reactants than products. That shows up in our data. Initially, we see this rapid decline in reactants, but the benefit is we have increase of products, right? So the increase of products comes at the expense of the reactants. Now, as time plays out, we realize that we reach this thing that we're calling equilibrium when those levels don't change anymore. And that's going to be, on a graph, that's going to be these flat regions when we're looking at concentration, that's what this is, versus time. So this would be equilibrium, we'll call it EQ. Our equilibrium constant that we've learned about is simply the ratio of the concentration of the products, right here, to the concentration of the reactants. So in this case, it's just M&Ms. 26 M&Ms over 14 M&Ms in the reactant side. So that gave us something real close to 1.9. That would be the equilibrium constant for this experiment. And again, that ratio is only true when we're looking at these flat regions here. I could find a K value at any point in the experiment. Let's say I came in early in the experiment and picked these points. My K value would be 10, right? That's 10 over 30, or my K would be 0.3. So a scientist could look at this and make those measurements and go, wait a minute, the equilibrium constant, according to the literature and what other scientists have done for this reaction, is 1.9. I'm only measuring 0.3. That tells the scientist then that that reaction has not come to equilibrium yet. It also tells them something else, and we're going to explore that next. Okay, so let's just go back and make sure that we understand the idea of a reversible reaction and equilibrium. We've been talking about this region right here, those flat lines. It could be misleading. You think that nothing is happening in this case, but in reality, we've learned that there's this idea of dynamic equilibrium. And what we have is essentially reactants are becoming products, and products are also then going backwards or to the left and becoming reactants. When these rates are equal, that's when we reach equilibrium. So the levels or the concentrations won't change because we're transferring back and forth the same amount of material in this case. Before you reach equilibrium, though, we do have, in some cases, maybe more reactants are becoming products. So maybe we could represent it this way with a shorter error from the products to the reactants. We could also have a time in the reaction where we actually have more products becoming reactants. So maybe our expression would look something like that. It's only at equilibrium when the levels are no longer changing. So let's just look at what happens. Remember, reactants and products are related to one another. One grows at the expense of the other. One shrinks at the benefit of the other. So as reactants become products, we're thinking about this happening. Reactants are going to decline, so maybe a big R goes into little r, right? And a little amount of products that we start with will become a big amount of products afterwards. So our equilibrium constant, or that ratio that we're talking about, would look something like this: a large P over a little r. What's happening as this happens is we're getting a larger value for K. Getting large K. What's happening in the reverse reaction is that, excuse me there, reactants are being formed at the expense of products. So we're moving in the reverse, or we're moving towards the left. So with time, we might start with a lot of product, and over time it's getting smaller, to the benefit of reactants. Reactants start off small and they get larger with time. So if we look at something moving forward in this reaction where more products are becoming reactants, then that's K is going to be given by a small p and a large R. So that gets closer to 0 or smaller. So let's see an example of how we'd be expected to put these things into context. Here's a question for our homework. For the reaction of carbon monoxide gas in a reversible reaction will produce carbon as a solid and carbon dioxide as a gas. The equilibrium constant is stated there, 7.7 times 10 to the negative 15. And we're asked, at a particular time, the following concentrations are measured. So a scientist comes in and actually measures these concentrations. We're asked, is the concentration at equilibrium, yes or no? And if not, which direction will the reaction proceed? That's asking, are we going to proceed to produce more reactants? Are we going to produce more products? Are we going to be moving to the left in the reverse direction or to the right in the forward direction? So here is our expression that we've learned prior to this for the equilibrium expression. The product concentrations, that's what those are in the brackets, raised to the number of moles of those products over the reactant concentrations, A and B, raised to the number of moles in those two. And man, that is really screwy. I don't know, doing this too fast. This should be raised to the C power. This should be raised, of course, to the D, A power, and B power. That is a little ugly, but it is correct. So here's how we'd interpret that, how we write our equilibrium expression for this problem. Our reactants, the traditional reactants, are CO. There's 2 moles of them, so we raise it to the 2 power. The carbon is in solid form, so we don't talk about its concentration. We're not going to use it in the equilibrium expression, but the carbon dioxide is in gas form, so it definitely should be there. There's a coefficient implied of 1 there, so we could think about raising it to the 1 power, but mathematically that doesn't matter. So crunching the numbers given to us, the concentration of carbon monoxide, carbon monoxide was 0.034, carbon dioxide 3.6 times 10 to the negative 17. Very small number, there's barely any of that. And we'll find that the answer would be about 3.1 times 10 to the negative 14. So remember, the scientists coming in and asked, is this reaction at equilibrium? And the literature value is saying the equilibrium constant should be that 7.7 times 10 to the negative 15th. Our scientist is finding his or her measurements gives us this. So they're not the same number. The answer then is, are we at equilibrium? No, we're not at equilibrium. So the next question is, well, what's happening if we're not at equilibrium? Which direction is the reaction proceeding? So if the scientist's goal was to make a measurement at equilibrium, the scientist just measured too early. What we notice is his or her measurement is greater than, right, 10 to the negative 14 is greater than 10 to the negative 15. So that means as time goes by, this ratio is going to get smaller. It's going to get closer and closer to 0. How would this ratio get smaller? This ratio will get smaller by R increasing, and remember that increases at the expense of the products. So when we're asked which direction would this proceed, we generally read a chemical equation. Whoops. Sorry about that. We generally read a chemical equation as putting reactants here and products on the right side. But what we're saying here in this instance is that we're looking at the reaction with the reactants becoming larger and the products becoming smaller. That would happen then by this path only, right? Products becoming the reactants. So we would say then that this favors the reverse direction, or we could say that we're moving in the left direction of the traditional equation. So you'll do a few more of those other problems, be expected to do those, but let's just take a look at the concept before we wrap up here. We are looking then at this ratio that we're calling the equilibrium constant, and it's simply the concentration of the products over the concentration of the reactants. So the concept would be this, read number 15, the equilibrium concentration of products is much greater than that of reactants. So products, really large, reactants, pretty small. That gives us a big value for K, or a K that is much larger than 1. That would be that instance. 16 reads this, the equilibrium concentration of products is much less than that of the reactants. So this might look this way. Big R, little p, that's going to give us a little k. or a K that is much less than 1. So that would be C. And finally, if we get a reaction that is where we have about the same amount of product as reactant, those values would be about the same size. That's going to give you something pretty close to 1. So that would be B. Okay, I hope this helps.